Okay, I'd like to go through a short example with you. This isn't in the lecture notes, but this is an example of the kind of question that you might expect in an exam, or certainly this might form part of a larger exam question. Now, by now, I'm hoping you've had a look through in the lecture notes the derivation of the energy conservation equation, which I asked you to read through yourselves, which is there in its completeness in the lecture notes. And you will notice that one of the things that comes up as part of that derivation of the energy conservation equation is Fourier's law of heat conduction. We need that to get the Q dot term, which appears as the starting point, the first law of thermodynamics. So here is the kind of question that might be tagged on to a larger question looking at, for example, energy conservation. Show that for a calorically perfect gas, we'll think about what that means in a moment, Fourier's law, which typically is written as Q dot is equal to minus K, where K here is the coefficient of thermal conductivity, grad T can be written as, is equivalent to, Q dot is equal to mu over PR, where PR is the Prandtl number, grad H, where H is enthalpy. Now you might see a question like this and start thinking to yourself about, well, where have I seen PR, or the Prandtl number, appear? Well, hopefully if you've done the exercise on non-dimensionalizing the energy equation, you will see that this non-dimensional coefficient Prandtl number appears in that. And PR is defined as mu Cp over K. Mu is dynamic viscosity, the coefficient of viscosity. Cp is specific heat capacity at constant pressure. K is thermal conductivity. So if you remember, we talked about this in the lecture this week. The Prandtl number gives you a measure or a feel for how important viscous effects are in comparison with thermal effects in the fluid. If viscous effects dominate, then the Prandtl number will be large. If thermal effects dominate, the Prandtl number will be small. And a typical number for most aerodynamic flows is that the Prandtl number is around about 0.7. So they're both of these effects are important. Next thing we perhaps need to think about is, okay, well, we've got enthalpy in this new version. I'm going to have to get this done quickly because I've only got 10% of battery left. Well, remember, H is the definition of enthalpy is internal energy E plus P over rho. So where are we going to start with this? Well, it's a calorically perfect gas. Now that's probably some clue of how we're going to go about this. Well, that means that we can use these two forms of equations of state. The ideal gas equation, P is equal to rho RT, and also that E is equal to CVT. These are true for a calorically perfect gas. They are equations of state because they relate state variables, variables like pressure and temperature and internal energy. So let's give this a whirl. Q dot. So we're going to start with Q dot, which is a vector field, the rate of change of heat, or the heat flux vector, is minus K grad T. Well, straight away from the definition of Prandtl number, we can take this and substitute it into this equation and write that Q dot is equal to minus mu Cp over PR grad T. So let's take this and see what this gives us. Well, we know that E can be written as CV. Oops. E is equal to CVT, and P over rho we can rewrite because of the ideal gas equation. So we can also use this to rewrite P over rho as RT. And it might make sense now to take out that factor of T. And we know that R, the specific gas constant, is simply Cp minus Cv, which brings us to this. Now we might have known that already, that we could write enthalpy for a calorically perfect gas as H is equal to Cpt. But if we didn't, the ideal gas equation and our definition of enthalpy as H equals E plus P over rho should get us to that point. Well, things are looking pretty good now because we can take the gradient of both sides of this equation. Cp is a constant, so we can bring that outside the grad operator. And now we're going to substitute this into our equation star over here. And state that Q dot is equal to minus mu over the Prandtl number grad H. There we are, as easy as that.